Welcome back to Math for Gamedev. For those of you tuning in for the first time, this is the series in which I cover math topics that I've found extremely practical as a game dev. I cover each topic through the demonstration of specific applied examples, focusing on the thought process behind how I approach a problem. For the entire oeuvre of what I'll be covering, check out the first video in the series. In this episode, we'll be covering trigonometry, which is the study behind the relationship between the angles and sides of a triangle. Again, just like with algebra, if you're watching this and want to go deeper into trig, search for stuff using the phrase introductory trigonometry or basic trigonometry. And honestly, good old Khan Academy might be the best for this one. So, in this video, let's imagine we're making a top-down shooter like Hyper Light Drifter here. Of course, in the game, when the player shoots, it should go to the reticle. A lot of game engines have a towards or a face function built in for vectors, so if you have something like that in your engine, go ahead and use it. However, if we look at the shotgun modification to the drifter shots, we need a way to spread the beams. No easy built-in function for that. In this video, we'll work out how to implement the basic shoot at reticle and the more advanced shoot with a spread. Now, it goes without saying that we want the projectiles to travel the same speed regardless of direction aimed, but I'll say it anyways because it's something we want. I'm going to cover all the trig we'll be using first because, well, once I do, this is actually a pretty straightforward problem. So before we proceed, let me first lay some groundwork. Meet our dear Stockholm Syndrome induced friend, the unit circle. What is it? It's just a circle of radius 1 that we'll use for trigonometry. Yes, I know I said triangles at the start, but trust me, it'll come in handy. The other piece of groundwork, mathematicians don't use degrees to measure angles. Why? Well, listen, the Greeks only had abacuses and compasses back then. Things were tough. Instead, mathematicians use radians. 1 pi in radians equals 180 degrees. But why? Well, I'll show you with our beloved friend, the unit circle. So, after some quick web searching, we know that the circumference of a circle, that is the length of one loop about a circle, is 2 pi times its radius. So, for the unit circle, that means its circumference is just 2 pi since its radius is 1. So, if we were to measure the length between any 2 points of the unit circle, or arc length, then that distance would be the same size of the corresponding angle in radians. Hopefully this makes sense to you and you can find it in your heart to forgive mathematicians. But again, if you ever need to convert between angles and radians or the other way around, just remember 180 degrees is equal to pi radians. And if you don't want to remember, just look it up, it's fine. So, trigonometry only works with right triangles. And if it ain't right, then it's the wrong type of triangle for trigonometry. Oh god, someone hit the crash zone. Now, what's a right triangle? Just any old triangle where one angle is 90 degrees, or in radians, pi over 2. Easy peasy. With the power of the unit circle, we can draw all right triangles, scaled up or down as needed, on the unit circle. Neato. Now let's take a look at a right triangle. Of course, it has 3 sides and 3 angles. It is a triangle, after all. The side opposite the right angle is the hypotenuse. And using one angle as our reference, one side is adjacent to that angle, and the other side is opposite, and we'll be referring to them as such. Of course, since the Greeks wanted a way to describe the relationships between the sides and angles of a right triangle, they discovered some nice functions that I'll show here real fast. If you ever get confused as to what's what, just remember SOHCAHTOA. And by that I mean the sine of an angle is the ratio of the lengths of the opposite side to the hypotenuse. The cosine of an angle is the ratio of the lengths of the adjacent side to the hypotenuse. And the tangent of an angle is the ratio of the lengths of the opposite side to the adjacent side. Hence SOHCAHTOA. And if we graph these curves from 0 to 360 degrees, or using radians, 0 to 2 pi, we see the following. Now, looking at the graphs of all of these functions, we can see that they repeat after a certain amount of time. This is called the period of the function. Sine and cosine repeat every 360 degrees, or in radians, 2 pi. And tangent repeats after every 180 degrees, or pi. And just like with algebra, when we were able to solve for x by using inverse operations to move things across the equal sign, sine, cosine, and tangent all have their own inverse operations. Arcsine, arccosine, and arctangent. tangent respectively. However, to successfully invert a function, we have to be able to draw a horizontal line anywhere on the graph and only hit one point on the curve, which we cannot do with the trig functions since they all repeat. So, to work around this, we only use parts of the original graphs for their inverse functions. Arcsine and arccosine are restricted to taking in values from -1 to 1, and arctangent will only return values from -90 degrees to 90 degrees, or in radians, -pi/2 to +pi/2. The inverse functions are written out in shorthand as either a sine, a cos, a tan, or they get a little -1 exponent on them. So what good is all this trig stuff? We just want to shoot something at a reticle. Well, I'll do a little movie magic and maybe it'll all click. As you can see, if we treat the player as the center of the unit circle and the reticle as a point on it, we can draw a right triangle, meaning we can use the position of the reticle relative to the player character to get the angle the player wants to shoot. So, in this situation, I think SOHCAHTOA, and using that I realize, hey, I know the opposite and adjacent sides of this triangle, but not the angle. So, writing it out, we get tan theta is equal to opposite over adjacent. Now I'll pump the brakes real fast. Oftentimes in trigonometry, instead of using English letters for variables, we use Greek letters, typically theta. After all, the Greeks did discover it, and mathematicians are nothing if not slaves to tradition. So here, theta is the mystery angle I do not know. Now since I want theta all by itself, I of course have to apply the inverse of tan to both sides of the equation to get it all by itself on one side. Now for a technical aside, most game engines have a function called atan2 that takes in the opposite and adjacent values independently and returns the angle we want from 0 to 360 degrees or 0 to 2 pi, it depends. If your game engine doesn't have atan2, you can always determine the actual angle using the signs of the opposite and adjacent values. Here I'll use atan2 since I want a value from 0 to 360 degrees, not -90 to 90 degrees. Now we have the angle the player wants to shoot, but we want to make sure the projectile travels the same speed regardless of direction. Again, let's say to ourselves, SOHCAHTOA, and look at our right triangle. The projectile will travel along the hypotenuse of the triangle, so we use cosine and sine to scale the projectile's speed properly. Cosine of theta will scale the x value. Sine of theta scales the vertical value. So when the player shoots, we spawn a projectile with horizontal speed equal to cos theta times actual projectile speed, and vertical speed equals to sine theta times actual speed. Hey, I'm editing right now and I realize I kind of just threw this statement out without any reasoning. I have supplied a link to a PDF that I wrote myself in the description. It should explain everything, so if you really want to know why we use sine and cosine, check it out.
Alright, let's see what happens when we press play.
Now, those of you thinking ahead should already have a rough idea of what we'll do to spawn a projectile with spread. Given the angle theta, we'll generate a bunch of random values, let's say 10 degrees, but in radians. About theta, let's call these theta 1 through theta 10. Then we just repeat the process we used for the single shot for each of these 10 spread out shots. Pop it inside a for loop and it'll be done lickety split. Now another technical aside, regarding implementing stuff, for all my editor value stuff, I use degrees and then I convert to radians as needed in code, and I recommend you do the same. If I look at some decimal number, unless it's 0 or 3.1415, I don't know what its angle is in radians. So hopefully now you can see how we use trigonometry to easily get lengths from angles and angles from lengths. Whenever you have a problem that deals with circles or angles, you might need trigonometry. It may take a little experience to discern how exactly, but if you just say to yourself, SOHCAHTOA, and draw out a right triangle, then you should be able to get a general idea of what to do. As always, think about what you want at the end and what you're given at the start, then use math to figure out how you're going to get from the start to the end. We could go a lot deeper into trigonometry, but I'll save it for later, meaning that once I'm finished with the episodes I have planned out already, I'll cover polar and spherical coordinates, which is a a way of describing things in Cartesian space using radiuses, angles, and the trig functions, which we just learned. And that's it for this episode. If any of you have any questions about anything I covered in this video, please leave a comment. Hopefully I can either help you understand it or at least point you towards better learning materials than my own. Next episode, we'll be covering a bunch of little functions and how you might find them useful. All you shady artists, pay attention next time. As always, thank you for watching, and I hope you have a good day. If you like the video, please give it a like, and if you want to follow along with this series or my devlogs once I get back to them, please subscribe. I'm a really small channel, so every little bit helps. You can also follow me on Twitter at dev_natsu. I share pictures of what I bake there right when I pop them out of the oven. And speaking of baking, let's look at what I made. So, this was my next try at macaroons, and as you can see, well, I'll switch to the non-Instagram angle. As you can see, they actually turned out really well this time. I was surprised, and I'm a little worried this was just beginner's luck because they honestly look really good. They have nice feet. They have a pretty good consistency on the shell. I mean, look at number 10. Well, I ran out of macaroon batter for that one, so I couldn't fully pipe out a 10th macaroon well. It didn't go well. However, I mean, if you look at the main 9, one's a little lopsided, but you know, I'm still happy. This was a very successful early attempt. Came out great, and I used regular instead of pastel food coloring. I used regular food coloring, so they got a much more yellow color. So you know, when you bite into them, yellow is basically lemon in dessert world. So you know, you bite into them, and you expect lemon, you get lemon. So if we took a look at the filling I used, again, I'm still working through all the lemons. So I made a lemon curd, and it didn't. But I think I made it the same day as when I was making these macaroons, and it was not ready to be used as a filling. It was still just too hot, too loose. So I panicked. I made a buttercream, and I mixed in the lemon curd with that. I learned recently how you're supposed to do it. You have the buttercream on the outside, curd on the inside. I didn't know that. So the filling is not the consistency I wanted here. However, it's still, again, it tastes great. The lemon curd tastes really good, and it's such an easy recipe, and you can just adjust it however you want, honestly. It's a very, very forgiving recipe, really tolerant. It's so easy, and plus, I have so many lemons still. I'm just making lemon curd every week, basically. It's really good, and it's a good, you can just put on anything. Have some ice cream, put on some ice cream, some bread, put on a slice of bread. It's a nice it's an easy dessert recipe, which there are not a lot of. But yeah, as you can see, I'm progressing well on macaroons, but this one was kind of beginner's luck. Not so successful in my next attempt, but still, I got good feed on it. Things worked out a lot better this time. So yeah, I'm gonna sign off. You guys should bake something. It's a great way to unwind either bread or something else like I'm doing right here. You always learn something new every time, and plus when you're done, you can share whatever you made with the people you care about. So yeah, that's it. See you guys later.